All right, friends, let's record a video that deals with two of my favorite friends, exponents and radicals. Let's talk about all the things that you're going to need to know about exponents and radicals to survive the last 2 years of high school and to thrive in the last 2 years of high school. Algebra can be your friend. Let's look at some rules of exponents. If you have a product, x to the m times x to the n, well, let's consider what this is. This is x times x times x times x, and there are m of those. And similarly, we have n of those. So altogether, we have a whole bunch of x's. How many? M plus n. Great. Great. Similarly, when we divide powers of the same base, we subtract the exponents. The rule is similar. So we didn't just make up a rule and hope that it works. We actually have a reason for it, and I think you can develop that reason on your own. Consider that for a moment. That means we have x to the m times x to the m times x to the m, and there are n copies of that. So what does that mean? Well, that means that I have m and another m and another m and so on until there are n m's. I have x to the mn. X to the mn. Couple other rules you should be aware of. You should know that if I have x times y to 1 power, well, that's the same as asking x to the m power and y to the m power. It's the same as raising x to the m and multiplying that by y to the m. And that almost makes sense because this is xy times x times y times x times y and so on. And there are m of those, but we can rearrange those so that there are a whole bunch of x's and then a whole bunch of y's. How many? M x's, m y's, and that's what you've got sitting right there. So I think that kind of speaks for itself. Similarly, x divided by y to the m is x to the m divided by y to the m. And then lastly but not leastly, what do you do if you have x to some negative power? What does that mean? Well, most people say, by definition, that's 1 over x to the positive power. But that's not true. That's not really by definition. It continues a pattern. And here's the pattern. If I have x squared, that's x times x. And if I have x to the first, that's just x. And if I have x to the 0, that's, well, we lose another factor of x. Going from here to here, we lose a factor of x. We divide by x. And then we go here to here, we divide by x again. So to go to this, we have to divide by x again, and so on. So really, this definition just keeps a pattern going that we're used to. So, consider the following. Let's simplify x to the 5th y squared over 2x squared y cubed all squared. Yeah, that'll do. Yeah, that'll do. Okay. So what do I do with that? Well, what I do with that is I want to expand this first. I want to deal with that set of parentheses. So I've got to square the 2. To square the 2, that's 2 times 2. Then I've got x squared squared. X squared squared is x to the 2 times 2. And y cubed squared is y to the 3 times 2. So now what? Well, now I've got x to the 5th divided by x to the 4th, that's x. I've got y squared over y to the 6th, that's a y to the 4th, but in the bottom, remember 6 minus 2, that ends up in the denominator, and then this 4 carries over. Similarly, if I were to say, let's multiply 3b cubed c all cubed times 9bc squared to the negative 2. Well, what happens there? Well, again, we're going to cube everything. So 3 cubed is 27. B to the 3 times 3 is b to the 9. That's a c cubed. Then we've got a negative 2, which means we're kicking stuff into the denominator with a positive 2 exponent. So 9 squared is 81. B squared is b squared. C squared squared. 2 times 2 is 4. So now what? Well, 27 divided by 81, well, that's 1/3. B to the 9th over b squared, 9 minus 2 is 7, and I've got a c cubed and a c to the 4th, that's bigger, 4 minus 3 is 1. Things you should know how to do. You should come to class ready to simplify, let's see, 2x squared over y quantity squared times y over x cubed cubed, and a squared b to the negative 2 all cubed times a cubed b to the negative 2. Negative 2. You should come to class ready to do that. Hey, a couple other things before we let you go. One is what to do with a fractional exponent. So by definition, x to the p over q is the qth root of x to the p, or if you like, the qth root of x to the p, but really, we use this definition. And we use this definition because it's easier to find roots, make numbers smaller, and then raise them to powers than it is to raise numbers to powers, make them big, and then try to find roots. Okay? Okay. So what to do in this scenario? In this scenario, we've got the 5th root of 32 squared. So how do I do that? Well, I've got to think of a number that I multiply by itself, by itself, by itself, by itself, so 5 copies of it, and get 32. Well, 1 times 1 times, that's 1, and 3 times 3 times, that gets really big, but 2 times 2 is 4, times 2 is 8, times 2 is 16, are you keeping track? Times another 2, that's 32. So the 5th root of 32 is 2, and we square it, and that's 4. Particularly on exams that are calculator inactive, it is helpful to know how to do things like 8 1/25ths to the 2/3. It is helpful to know how to do that, and the way we do that is we take a cube root and square it. So when we take a cube root of a fraction, we take the cube root of the top, that's 2, and then the cube root of the bottom, that's 5, and we square it, and that's beautiful. You should come to class ready, willing, and able to do 100 to the negative 3 halves and 256 to the 3/4 times 16 to the negative 3/4. You should know how to do those based on what we've just talked about. One more thing we should talk about. We should talk about radicals. We should talk about how radicals work and why they are the bane of so many algebra students' existence. So consider the following. Let's simplify. Let's simplify radical 18 plus radical 50 plus radical 72. Now, you would think that we just add them up. 72 and 18 is 90. That's 140. But no, that's not how things work. That's not how things work. Because we can only add radicals when the radicands are the same. And that's not the case here. We've got an 18 and a 50 and a 72. They're totally different. So instead, we simplify the radicals. And we simplify the radicals by breaking them up into a perfect square and some leftover factor. And you know all your perfect squares, 1, 4, 9, 16, 25, 36, and so on. And in every case, we are looking for the greatest perfect square that goes into our radicand. And in this case, the greatest perfect square that goes into 18 is 9. What's left over? Well, 9 goes into 18 twice. Similarly, looking for a perfect square that goes into 50, and I'm sure you can scan that list and come up with 25. How many times does 25 go into 50? Well, it goes in twice. And then I think you know where we're going from here. 1 surely goes in, 4 surely goes in, 9 surely goes in, but we can do better than that. 36 divides 72. It divides 72 twice. So now I think to myself, the square root of 9 is 3, and the square root of 25 is 5, and the square root of 36 is 6. So if I have 3 radical 2's and somebody gives me 5 radical 2's for my birthday, and somebody gives me 6 radical 2's because they like me, that's 14 radical 2's. And if you were to pull out a calculator and type in radical 18 plus radical 50 plus radical 72, and then you were to clear the calculator and you were to type 14 times the square root of 2, you would get the same answers in both cases. You would get the same answers. So what's important to remember when you're simplifying radicals? You must have the same radicand to simplify. You must have the same radicand to simplify, which is why if you try to simplify this, then what you will find is this is easy enough. 100 is a nice perfect square, goes in twice. 4 is a nice perfect square, goes in twice. 25 is a nice perfect square, goes in 3 times. Sure, square root of 100 is 10, and square root of 4 is 2, and square root of 25 is 5, but these don't simplify. I can combine these. I can get 12 radical 2. But I cannot simplify beyond this because I cannot combine radicals where the radicands are different. I'm not allowed. Things you should know how to do as a little self-check. You should know how to simplify 2 radical 63 minus radical 28. You should know how to simplify 5 radical 27 minus radical 75 plus radical 20. And you should know how to simplify radical 2 minus radical 3 squared. This is a nice review of how to multiply a binomial by a binomial. Hey, one more crazy rule. And the crazy rule is no radicals in the denominator of a fraction. None. No radicals in the denominator of a fraction at all. So if you see a fraction and it has a radical in the denominator, you are supposed to yell loud warnings that such things may not happen. If you see a fraction with a radical in the denominator, you are supposed to scream loudly that there cannot be a radical in the denominator. Now, there are two different ways to deal with these problems. The question on the left, this is a monomial. And when we have a monomial, it's really easy. We just multiply and divide by the radical 5. And the reason that works is because radical 5 times radical 5 is radical 25. I mean, the square root of a number times the square root of that same number is the number. Then your numerator becomes a distribution problem. Radical 5 times 1 is radical 5. Radical 5 times radical 3 is radical 15. And that doesn't simplify. That doesn't combine. Those terms can't combine. The radicands are different. And so we're done at that point. If, however, there's a binomial denominator with a radical in it, then the key there is to use the conjugate. And the conjugate of 2 minus radical 5 is 2 plus radical 5. And we multiply and divide by that conjugate. The conjugate of a plus radical b is a minus radical b. The conjugate of a minus radical b is a plus radical b. And the reason that works is that when you multiply this binomial by that binomial, you get 4, you get minus 5, and then look what happens. You get a negative 2 radical 5 and a positive 2 radical 5. They drop out. They drop out. The radicals disappear. That's why the conjugate thing works, and that'll work every time. Your numerator, that's easy. That's 2 plus 2 radical 3 plus radical 5 plus radical 15, and I ran out of space. But you know that gets extended because that's the kind of folks you are. And so what ends up happening, I get 2 plus 2 radical 3 plus radical 5 plus radical 15 over 4 minus 5 is negative 1. And if I even want to make things nicer than that, I'm done. You should practice on your own. You should know how to rationalize that denominator. And you should know how to rationalize that denominator. That's the process we just did. This is a process called rationalizing the denominator. Rationalizing the denominator. That's a mess, isn't it? The denominator. All right? Those are things you should know how to do at this point. Okay. Well, fantastic. Thanks for experiencing exponents and radicals. Who knows what happens next?